You have never once in your life been still, not while sleeping, not while standing motionless, not for a single second. Right now, the ground beneath you is carrying you through space at speeds the human brain was never built to intuit. Earth's rotation alone moves you sideways at more than 1,000 miles per hour if you are standing near the equator, faster than the speed of sound, faster than a rifle bullet, and yet you feel absolutely nothing. But that is only the smallest layer of the motion. At the same time, Earth is orbiting the Sun at roughly 67,000 miles per hour, tracing a path of nearly 584 million miles every year. The solar system itself is sweeping around the center of the Milky Way at more than 500,000 miles per hour, completing one galactic orbit roughly every 225 million years. The last time Earth occupied this region of the galaxy, dinosaurs had not yet appeared, and even that is not the fastest thing happening. The Milky Way itself is moving, so is every nearby galaxy around it. All of them are being pulled toward a gravitational region so massive and so obscured that astronomers spent decades struggling to understand whether it even existed at all. They eventually named it the Great Attractor, and whatever it is dragging our entire galaxy through the universe at more than 1 million miles per hour. No wind accompanies any of this, no vibration, no sensation of movement whatsoever. The universe moves at catastrophic speeds in complete silence. Quick favor before we continue. If you find yourself coming back to videos like these, hit subscribe so you don't miss the next one. It makes a bigger difference than you might think. Now, let's begin. If you close your eyes in a quiet room, the world feels still. The floor beneath you feels fixed. The walls feel permanent. Even now, your body assumes rest as the natural condition of existence. But physics tells a very different story. Stillness does not truly exist. Here on Earth, we measure movement against familiar objects. A highway sign slips past a car window. A train crosses a station platform. A plane moves above a coastline. Speed feels intuitive because the background appears motionless. We always compare motion to something else. Space removes that comfort completely. Beyond Earth, there is no cosmic pavement beneath the universe. No giant marker hangs in darkness declaring absolute rest. Every star moves, every galaxy drifts. Even the emptiest regions between galaxy clusters continue changing over unimaginable stretches of time. This creates one of the strangest truths in modern physics. Every velocity in the cosmos is relative, meaning it depends entirely on what you choose as the reference point. Relative to the Sun, Earth moves around 67,000 miles per hour. Relative to the center of the Milky Way, the speed becomes vastly larger. Relative to nearby galaxies, the numbers shift again. And relative to the cosmic microwave background, the ancient radiation left behind by the Big Bang, Earth moves at roughly 1.85 million miles per hour. Which speed is the real one? All of them are, but none are absolute. This is not confusion in the measurements. It is the structure of reality itself, described in 1905 by Albert Einstein through special relativity, the theory explaining how motion, time, and distance behave when objects move relative to one another. Einstein realized something unsettling. The universe does not provide a preferred frame of rest. Physics works the same whether you stand on Earth, drift aboard a spacecraft, or orbit a distant star. Motion can only be described compared to something else. You can imagine it like layers moving together. A passenger walks through a train car. The train crosses a continent. The continent rotates with Earth. Earth circles the sun. The sun orbits the galaxy. The galaxy itself falls through the larger cosmic web. Each layer carries the smaller layers inside it, producing multiple simultaneous motions at once, and all of them are real right now without feeling even the slightest vibration. You are participating in every one of these motions together. Your heartbeat remains steady while your planet rotates beneath the atmosphere, while the solar system sweeps around the Milky Way, while the galaxy itself drifts through expanding space. The deeper we look, the stranger the scale becomes, because Earth does not possess one speed through the universe. It possesses many, stacked inside one another like nested currents in an ocean too large for the human mind to fully picture. And the smallest layer of that motion begins directly beneath your feet. Long before clocks existed, people tracked time by shadows. A stone pillar shortened at noon, then stretched again toward evening. The sun appeared to cross the sky once each day, steady and predictable, but the motion was never the sun's alone. The ground beneath those shadows was already turning. Earth completes one full rotation every 23 hours, 56 minutes, and 4 seconds. This is called a sidereal day, meaning a full spin measured against distant stars instead of the sun. The familiar 24-hour solar day is slightly longer because Earth moves along its orbit while rotating, forcing the planet to turn a little farther before the sun returns to the same position overhead. The difference is small, barely noticeable, yet it reveals something profound. Even the rhythm of day and night depends on multiple motions unfolding simultaneously. At the equator, Earth's rotational speed reaches approximately 1,037 miles per hour. That is faster than the speed of sound at sea level, which averages around 767 miles per hour under normal atmospheric conditions. Someone standing near Earth's equator is moving faster than a supersonic jet while feeling absolutely nothing. No wind announces it, no vibration follows, but the speed changes across the planet. At 45 degrees latitude, rotational velocity drops to roughly 733 miles per hour. Near the poles, lateral movement disappears almost entirely. You still rotate with Earth there, but you mostly spin in place, tracing tiny circles around the axis itself. This constant rotation reshapes the planet physically. Earth is not a perfect sphere. It is an oblate spheroid, meaning slightly flattened at the poles and wider around the equator. Centrifugal effect, the outward tendency produced by rotation, pushes material outward over immense spans of geological time. The result is measurable. Earth's equatorial diameter exceeds its polar diameter by about 26 miles. Satellites notice this imbalance constantly. Low orbit spacecraft experience orbital precession, a slow rotation of their orbital paths caused by the uneven pull from Earth's equatorial bulge. Engineers must account for it precisely when planning missions lasting months or years, but the spin itself is slowly fading. The moon pulls on Earth's oceans through gravity, generating tides that create friction against coastlines and seafloors. This process steals rotational energy from Earth at a rate of roughly 1.4 milliseconds per century. Tiny changes accumulate across deep time. Around 1.4 billion years ago, a full day lasted only 18 hours. About 620 million years ago, coral growth rings recorded nearly 400 days in a single year. The future continues that progression silently. Eventually, Earth will become tidally locked to the moon, meaning one hemisphere will permanently face it, while the other never will. The moon already exists in this state, which is why the same lunar face always hangs above us. Earth's rotation may be the smallest motion in this vast chain of cosmic velocities, but without it, the atmosphere would behave differently, oceans would circulate differently, and life itself would unfold beneath an entirely altered sky. A pilot leaving Tokyo for Los Angeles does not fly across a motionless world. Beneath the aircraft, the planet turns continuously, carrying oceans, continents, and atmosphere eastward through space. The route curves subtly across maps because the surface itself is moving during the journey. This shifting frame creates the Coriolis effect. The Coriolis effect is the apparent bending of motion across a rotating surface. Different parts of Earth move at different rotational speeds, so objects traveling long distances drift relative to the ground beneath them. Near the equator, the surface moves fastest. Closer to the poles, movement slows dramatically. Air feels this difference constantly. In the northern hemisphere, moving air curves toward the right. In the southern hemisphere, it bends toward the left. The effect does not push directly like a physical force. Instead, it emerges because Earth rotates underneath moving objects while they travel. The atmosphere organizes itself around this invisible geometry. When warm ocean water feeds rising humid air, pressure begins to fall. Surrounding winds rush inward toward the low pressure center, but Earth is rotating beneath those winds while they move, causing the air to spiral rather than collapse straight inward. Hurricanes in the northern hemisphere rotate counterclockwise. Cyclones south of the equator rotate clockwise. Their shape comes from planetary motion. Without the Coriolis effect, global weather would behave completely differently. Air would simply stream from high pressure regions toward low pressure regions in mostly straight paths. Large rotating storm systems would struggle to form. Jet streams would weaken or vanish. Climate zones across continents would reorganize into unfamiliar patterns. But the effect only dominates at large scales. A common myth claims water draining from sinks or bathtubs spins differently across hemispheres because of Earth's rotation. In reality, the Coriolis effect at those scales is far too weak. Tiny imperfections in the container shape or the initial motion of the water completely overwhelm it. The oceans, however, obey it relentlessly. The Gulf Stream carries warm tropical water northward from the Gulf of Mexico along the eastern coast of North America before crossing the Atlantic toward Europe. The Coriolis effect helps steer and maintain this immense current. Without that transport of heat, winters across Western Europe would become dramatically colder despite similar latitudes to parts of Canada. Human technology must obey these motions too. Intercontinental ballistic missiles travel thousands of miles through Earth's atmosphere while the planet rotates beneath them. Military targeting systems must calculate Coriolis deflection carefully. Ignoring Earth's spin would cause a missile to miss its destination by many miles. Even long range artillery accounts for it. In 1918, during the First World War, Germany's Paris gun fired shells over 75 miles away. Engineers discovered that Earth's rotation altered the shell trajectories enough to require measurable corrections. So the planet's spin reaches into storms, ocean currents, navigation, aviation, and warfare alike. We rarely notice it directly, yet every swirling cloud pattern seen from orbit carries the signature of a rotating world moving silently beneath the atmosphere. Every January, Earth reaches a point in space it will never visit again. The planet crosses invisible coordinates beside the Sun, moving through darkness at tremendous speed, tracing a path so enormous that human intuition barely holds onto it. We call this path an orbit. Earth circles the Sun at an average velocity of about 67,000 miles per hour, or roughly 18.5 miles every second. During the time it takes to breathe once, the planet has already traveled dozens of miles through space. Over the course of a single year, the total distance becomes approximately 584 million miles. The scale escapes ordinary comparison. If stretched into a straight line, that yearly journey would span the distance between Earth and Jupiter several times over. Yet from the ground, the motion remains hidden behind the calm rhythm of sunrise and sunset. But the orbit is not perfectly circular. In 1609, the astronomer Johannes Kepler published the laws describing planetary motion after years studying observations gathered by Tycho Brahe. Kepler discovered that planets move in ellipses, meaning slightly flattened circles, with the sun offset from the center rather than sitting perfectly within it. That subtle asymmetry changes Earth's speed continuously. Around January 3rd, Earth reaches perihelion, its closest approach to the sun. At that point, the planet sits approximately 91.4 million miles away and moves slightly faster through space. Around July 4th comes aphelion, the farthest point when Earth drifts about 94.5 million miles from the Sun and slows modestly. The difference approaches 2,000 miles per hour. No human sense can detect it. Instruments can. This changing distance creates one of astronomy's most persistent misunderstandings. Many people assume seasons occur because Earth moves closer to or farther from the Sun. The opposite timing between hemispheres proves otherwise. When the northern hemisphere experiences winter during January, Earth is actually nearest the Sun. At the exact same time, Australia and much of South America experience summer heat. The true cause lies elsewhere. Earth's axis tilts by approximately 23.5 degrees relative to its orbital plane. During northern hemisphere summer, that hemisphere leans toward the sun, causing sunlight to strike more directly and linger longer each day. 6 months later, the geometry reverses. Sunlight arrives at steeper angles and daylight shortens. The seasons emerge from orientation, not distance, but even the orbit itself refuses permanence across deep time. The immense gravity of Jupiter and Saturn subtly disturbs Earth's path over tens of thousands of years. The ellipse stretches and relaxes. The axial tilt shifts slightly. The direction of the tilt slowly wobbles through space. These overlapping variations accumulate gradually, altering how sunlight distributes across the planet over geological ages, and eventually, those tiny orbital changes become powerful enough to reshape the climate of the entire world. In northern Greenland, ancient ice lies stacked in layers older than human memory. Snow fell there tens of thousands of years ago, compressed slowly into blue crystal beneath its own weight. Buried inside are tiny bubbles of prehistoric air, frozen samples from worlds long vanished. Those frozen layers record a planet that does not keep a perfectly steady climate. Earth drifts through recurring cycles of cold and warmth because its motion around the sun changes subtly over immense spans of time. The shifts are small at any given moment, but over thousands of years, they accumulate into transformations powerful enough to bury continents beneath ice. Astronomers divide these variations into three overlapping motions called Milankovitch cycles. The first is eccentricity, meaning the changing shape of Earth's orbit. Over roughly 100,000 years, the orbit shifts from more circular to more elliptical and then gradually returns again. This alters the difference between Earth's nearest and farthest distances from the Sun during each year. The second cycle is obliquity, the variation in Earth's axial tilt. That tilt slowly changes between about 22.1 degrees and 24.5 degrees across approximately 41,000 years. Larger tilt angles intensify seasons, smaller tilts soften them. Then comes precession. Earth's rotational axis slowly wobbles like a spinning top over about 26,000 years. This changes which hemisphere points toward the sun during perihelion, subtly redistributing seasonal sunlight between north and south. Individually, each cycle seems modest. Together, they reshape climate history. These patterns were calculated by Serbian mathematician Milutin Milankovic during the early 20th century. While imprisoned during the First World War, he spent years performing enormous astronomical calculations entirely by hand, using paper, pencil, and persistence to map how orbital variations influence sunlight across Earth. His central insight was deceptively simple. Ice ages begin when northern summers become too cool to melt all the previous winter's snow. Small patches of surviving ice reflect more sunlight back into space because bright surfaces bounce radiation away efficiently. This increased reflection cools the planet further, allowing even more snow to survive the following summer. The process feeds itself gradually. Century after century, glaciers expand. Around 20,000 years ago, during the last glacial maximum, ice sheets up to 2 miles thick covered regions that are now Chicago, Toronto, Stockholm, and London. Sea levels dropped dramatically as enormous quantities of water became trapped in continental ice. Human populations survived near the edges of these frozen worlds. But Milankovitch's theory remained controversial for decades because direct evidence was missing. That changed in 1976 when deep-sea sediment cores revealed repeating climate cycles occurring at precisely the intervals his calculations predicted. The timing matched almost perfectly. Today, we live inside an interglacial period, a warmer interval that began approximately 11,700 years ago. Every city, empire, language, and agricultural civilization in human history emerged during this unusually stable climatic window. Without it, civilization might never have formed at all. Under natural conditions, another major glacial period would likely begin roughly 50,000 years from now. But human greenhouse emissions may already have altered the cycle enough to postpone that frozen future indefinitely. The night sky feels fixed because human lives are short. Constellations seem permanent. Orion still stands where ancient civilizations once saw him. The Milky Way still stretches across darkness like a pale river of light, but the entire sky is in motion. So are we. The solar system is orbiting the center of the Milky Way galaxy at roughly 514,000 miles per hour. The sun carries every planet with it, including Earth, along a vast galactic trajectory impossible to perceive from the ground below. At that speed, one full orbit still takes about 225 million years. Astronomers sometimes call this a cosmic year or galactic year. It is a unit so immense that human history disappears inside it almost completely. Recorded civilization occupies only a tiny fraction of 1% of a single galactic orbit. The previous cosmic year ended in a profoundly different world. Around 225 million years ago, the supercontinent Pangaea had only begun breaking apart. Dinosaurs had not yet risen to dominance. The Permian extinction, the most devastating biological catastrophe in Earth's history, had recently erased approximately 96% of marine species and around 70% of land vertebrates. Earth itself was recovering slowly. Since the planet formed roughly 4.5 billion years ago, it has completed only about 20 journeys around the Milky Way, 20 circuits through the galaxy, 20 passages around the gravitational center, shaping our entire stellar neighborhood. But the motion is not a flat circle. The solar system also oscillates above and below the galactic plane while orbiting, drifting through the Milky Way in a slow vertical rhythm. Roughly every 30 to 35 million years, we cross the dense midplane of the galaxy before gradually rising away again. This movement carries us through changing cosmic environments. Near the galactic plane, stars become more crowded, gravity fields grow more complex, vast clouds of gas and dust thicken between stellar systems. Some scientists suspect these passages may influence life on Earth itself. Physicist Richard Muller of the University of California, Berkeley, proposed that galactic plane crossings could disturb the distant Oort cloud, a massive shell of icy bodies surrounding the solar system far beyond Pluto. Gravitational disruptions there might send increased numbers of comets inward toward the planets. The idea remains debated. No consensus exists linking galactic crossings directly to extinction cycles. Yet several major extinction events appear to align intriguingly with modeled timings of these oscillations through the Milky Way's dense interior. The galaxy may occasionally alter conditions on Earth from tens of thousands of light years away. And all of this motion traces back toward a hidden center. Deep within the Milky Way, concealed behind immense clouds of dust and gas, lies the object governing the orbit of the entire solar system. Every star visible tonight, every planet, every comet, every drifting fragment of ice and rock, circles that unseen gravitational anchor together through the dark. Radio waves from the center of the Milky Way arrive at Earth after crossing more than 26,000 light-years of space. They emerge from a region hidden behind dense curtains of interstellar dust, a place invisible to ordinary telescopes for most of human history. Something enormous lives there. Astronomers call it Sagittarius A star, written Sagittarius A with an asterisk. Despite the name, it is not a star at all. It is a supermassive black hole containing roughly 4 million times the mass of the Sun, compressed into a region comparable in size to Earth's orbit. For decades, scientists could not observe it directly. Visible light from the galactic center is blocked almost completely by gas and dust spread across the Milky Way's inner disk, but infrared light can penetrate much of that obscuring material. Beginning in the 1990s, teams led by Reinhard Genzel in Germany and Andrea Ghez in the United States tracked stars moving near the hidden center with extraordinary precision. Those stars revealed the invisible object. One star in particular, designated S2, became crucial evidence. S2 completes a full orbit around Sagittarius A star every 16 years. At closest approach, it races through space at approximately 11 million miles per hour, while passing only about 17 light hours from the black hole itself. Its trajectory leaves little room for alternative explanations. Only an object with millions of solar masses compressed into an extremely tiny volume could produce such motion. In 2020, Genzel and Ghez received the Nobel Prize in Physics for this work, which transformed the black hole from theoretical inference into measured reality. Then came an even more remarkable image. In 2022, the Event Horizon Telescope collaboration released humanity's first direct view of Sagittarius A star. The image showed a glowing ring of superheated gas surrounding a dark central shadow approximately 44 million miles wide. The black hole itself remains invisible because gravity there bends space-time so severely that light cannot escape. Once it crosses the event horizon, the boundary beyond which return becomes impossible. But Sagittarius A star is strangely quiet today. Many supermassive black holes consume enormous amounts of gas, producing brilliant radiation visible across billions of light years. Our galaxy's central black hole currently feeds only weakly, yet evidence suggests it was far more active in the relatively recent past. Around 3.5 million years ago, Sagittarius A star erupted violently, releasing colossal jets of high energy particles above and below the galactic plane. Those outflows created structures now called the Fermi bubbles, immense lobes of gamma ray emission extending roughly 25,000 light years in both directions. They were discovered only in 2010. At the time of that eruption, Australopithecus still walked the savannas of eastern Africa. Early human ancestors existed beneath African skies, while the center of the Milky Way unleashed energy on scales difficult to imagine. And through all of it, the galaxy continued orbiting this hidden gravitational center. Every star visible tonight participates in that motion, every drifting cloud of gas, every planet, the sun itself, including the one beneath your feet. Seen from above, the Milky Way would not resemble a smooth disk of evenly scattered stars. It would appear structured, curved, almost organic, with luminous arms winding outward from a bright central bar across 100,000 light years of space. Our galaxy is a barred spiral galaxy. That shape emerges from motion. Vast numbers of stars orbit the galactic center together, yet the spiral arms are not rigid structures turning like blades on a fan. They are density waves, regions where gas, dust, and stars become temporarily crowded together as they orbit. The distinction matters deeply. A useful comparison comes from highway traffic. Cars slow and bunch together around congestion, then spread apart once they pass through it. The traffic jam itself persists even though the individual cars continuously enter and leave it. Spiral arms behave similarly. Stars drift into denser regions, linger for millions of years, then emerge again into less crowded galactic space. The Sun currently resides within, or perhaps just outside, a smaller structure called the Orion Spur. This minor arm lies between two much larger spiral features, the Sagittarius arm inward toward the galactic center and the Perseus arm farther outward. That location may not be trivial. Major spiral arms are intense regions of star formation. Dense clouds collapse there under gravity, igniting new stars in enormous numbers. Massive young stars burn violently and briefly, flooding surrounding space with radiation before exploding as supernovae. The environment becomes brighter, harsher, and more unstable. Our position between major arms may have offered unusual long-term calm. Earth has experienced billions of years without a nearby supernova sterilizing the planet's surface. Some astronomers suspect this relative isolation helped complex life evolve gradually without repeated catastrophic interruptions from intense cosmic radiation. But the solar system does not remain stationary relative to the arms. Roughly every 100 to 150 million years, the Sun likely passes through one of the Milky Way's larger spiral arms during its galactic orbit. These crossings bring the solar system into denser interstellar regions filled with more stars, more gas clouds, and potentially greater exposure to cosmic rays. Several researchers have proposed links between these crossings and periods of elevated extinction or evolutionary pressure on Earth. The evidence remains uncertain, partly because reconstructing the solar system's precise galactic path across hundreds of millions of years is extraordinarily difficult. The Milky Way itself remains partly mysterious. Astronomers estimate the galaxy contains somewhere between 200 billion and 400 billion stars. Even that enormous range reflects the challenge of counting objects hidden behind thick dust clouds spread through the galactic disk. The disk extends about 100,000 light-years across, while remaining only roughly 1,000 light-years thick near the Sun's location. Yet, it is not perfectly flat. Observations using Cepheid variable stars in 2019 confirmed that the outer regions warp and flare upward and downward like the edges of a distorted vinyl record. So even the galaxy carrying us through space is not stable geometry frozen in place. It bends, shifts, pulses with star birth, and slowly rearranges itself across cosmic time while we travel quietly inside it. On clear autumn nights in the northern hemisphere, a faint blur appears within the constellation Andromeda. To the naked eye, it looks fragile, almost insignificant, barely distinguishable from the surrounding darkness. Yet that dim patch contains roughly 1 trillion stars, and it is moving toward us. The Milky Way does not drift through space alone. It belongs to a collection of more than 54 galaxies called the Local Group, spread across approximately 10 million light years. Most members are small dwarf galaxies orbiting larger companions. Two dominate the structure completely: the Milky Way and the Andromeda Galaxy. Gravity has been drawing them together for billions of years. Andromeda currently lies about 2.537 million light years away and approaches the Milky Way at roughly 250,000 miles per hour. The motion was first measured through Doppler shift, the stretching and compression of light caused by movement through space. More recent observations from the Hubble Space Telescope and the European Space Agency's Gaia spacecraft refined the trajectory with extraordinary precision. The conclusion became unavoidable. The collision has already begun, not because the galaxies touch now, but because gravity committed them to impact long ago. The first close encounter will likely occur in approximately 4.5 billion years. Long before that moment, the night sky will transform. Around 3.75 billion years from now, Andromeda will appear vastly larger from Earth than it does today. Its bright central core and extended spiral structure will stretch across enormous sections of the sky, far wider than the full moon, glowing softly through the darkness like a second Milky Way approaching head-on. But galaxy collisions unfold slowly. The first pass will take hundreds of millions of years. The galaxies will sweep through one another, distort under gravity, separate temporarily, then fall back together again. Tidal forces, meaning gravitational stretching caused by uneven pulls across large distances, will tear apart the familiar spiral arms of both galaxies. Stars themselves will almost never collide directly. Galaxies are mostly empty space. Even during a merger of this scale, the average distance between stars remains immense. But gravitational interactions will rearrange countless stellar orbits. Some stars will be flung outward into intergalactic darkness. Others will plunge toward the new galactic center. Eventually, the Milky Way and Andromeda will settle into a single, giant elliptical galaxy, sometimes nicknamed Milkomeda. The structure will look very different from today's graceful spirals. Most of the cold gas required for star formation will already be consumed or scattered away. New stars will become increasingly rare. Older reddish stars will dominate the merged galaxy's light. NASA simulations suggest the Sun has roughly an 85% chance of surviving the merger without direct catastrophe, but it will likely end up in an entirely different region of the final galaxy. Earth, however, almost certainly will not witness the ending. Around 5 billion years from now, near the time the merger reaches its later stages, the Sun itself will expand into a red giant, transforming the inner solar system long before the galaxies finish reshaping the sky above it. Galaxies gather the way droplets gather on glass. Gravity pulls matter into clusters, clusters into larger formations, and those larger formations into structures so immense that individual galaxies begin to resemble grains of dust suspended inside them. The local group is one of those droplets. Our galactic neighborhood contains more than 54 known galaxies spread across roughly 10 million light years. Most are small dwarf systems orbiting larger companions. The Milky Way and Andromeda dominate the group gravitationally, while dozens of lesser galaxies drift around them like satellites. But the local group itself is moving. The entire collection falls toward a much larger structure called the Virgo supercluster, a vast concentration of galaxy groups and clusters stretching approximately 110 million light years across. Near its center lies the Virgo cluster, a dense assembly containing more than 1,300 galaxies packed into a relatively compact region about 53.8 million light years away. The local group moves toward that cluster at roughly 150 miles per second. Even at those speeds, the journey unfolds across incomprehensible timescales, and there is no guarantee we will ever arrive. The universe itself is expanding, and that expansion accelerates over time. Gravity pulls the local group inward toward Virgo, while cosmic expansion simultaneously stretches space outward between large structures. The outcome remains uncertain. For decades, astronomers treated the Virgo supercluster as one of the largest meaningful structures in the nearby cosmos. But in 2014, a team led by Brent Tully at the University of Hawaii changed that picture dramatically. They did not map galaxies by position alone. Instead, they mapped motion. Using enormous data sets of galaxy velocities, the team reconstructed how matter flows through space under gravity. Their analysis revealed that the Virgo supercluster was not isolated at all. It was merely one branch inside something vastly larger, an immense interconnected basin of galactic motion. They named it Laniakea. The word comes from Hawaiian and means immeasurable heaven, a fitting name for a structure spanning roughly 520 million light years and containing the mass of approximately 100 million billion suns. Within it drift around 100,000 galaxies, all participating in slow gravitational currents across the cosmic landscape. The Milky Way occupies a relatively quiet outer region of this enormous structure. Far from the crowded interior, our galaxy sits near the periphery, where local conditions remain comparatively calm. Yet the motions of galaxies throughout Laniakea reveal something remarkable. When plotted in 3 dimensions, their velocities converge inward toward a single region deep within the structure. Like rivers flowing downhill, galaxies stream toward the same destination. That convergence point exerts enough gravitational influence to shape the motion of entire superclusters across hundreds of millions of light years. We cannot fully see it clearly because the dense disk of the Milky Way blocks much of the view in that direction. But its pull is measurable. And somewhere beyond the obscuring dust of our own galaxy lies one of the strangest gravitational mysteries humanity has ever discovered. Maps of the universe once appeared deceptively orderly. Galaxies clustered here, spread thin there, and drifted apart within the expanding cosmos according to gravity and distance. But when astronomers began measuring large-scale galactic motion carefully, they found something unsettling. Entire regions of space were flowing in the same direction. The Milky Way, Andromeda, the Virgo cluster, and thousands of surrounding galaxies all appear to move toward a shared gravitational destination at roughly 1.3 million miles per hour. The motion persists even after accounting for cosmic expansion and local gravitational interactions. Something enormous is pulling on us. Astronomers named this mysterious region the Great Attractor. It lies approximately 150 to 250 million light years away in the direction of the constellations Centaurus and Norma. Yet, for decades after researchers proposed its existence during the 1970s, they could not observe it directly. Our own galaxy stood in the way. The dense disk of the Milky Way blocks roughly 20% of the observable sky from ordinary optical telescopes. Thick clouds of dust and enormous concentrations of stars absorb visible light almost completely in that direction. Astronomers call this obscured region the zone of avoidance because early galaxy surveys simply avoided it. But gravity revealed that something massive existed behind the veil. Using radio telescopes and X-ray observatories, scientists slowly penetrated the obscuring material. They uncovered a huge concentration of galaxies centered around the Norma cluster, a dense galactic assembly hidden almost directly behind the Milky Way's plane. For a time, the mystery seemed solved, but the numbers refused to cooperate. The visible mass of the Norma cluster alone could not generate the observed gravitational pull affecting nearby galaxies. The calculations consistently fell short. Too much motion existed for the amount of detectable matter present. So astronomers looked deeper. In 2016, observations from the Parkes Radio Telescope in Australia revealed an enormous, previously unknown structure concealed behind the zone of avoidance. Researchers identified 883 uncatalogued galaxies concentrated within a region that had once appeared nearly empty on sky maps. The discovery became known as the Vela supercluster. It significantly increased the estimated mass hidden behind the Milky Way. Yet even Vela may not fully explain the motion observed across Laniakea. Some astronomers suspect the much more distant Shapley supercluster, located roughly 650 million light-years away, contributes additional gravitational influence across enormous cosmic distances. The true source may be distributed across multiple overlapping structures rather than one isolated object. What remains undeniable is the motion itself. The Milky Way is being drawn somewhere through space at speeds difficult to comprehend, along with hundreds of thousands of surrounding galaxies. And the destination remains only partially understood because the structure obscuring our view is the galaxy we inhabit. To understand where we are going, we first have to see through ourselves. Even now, new telescopes continue uncovering hidden galaxies behind the Milky Way's dust, slowly revealing portions of the cosmic landscape that remained invisible for all of human history. Ancient navigators once crossed oceans with incomplete maps. Entire coastlines were missing. Vast regions carried labels warning that nothing reliable was known beyond them. Modern astronomy inherited a surprisingly similar problem, not across oceans, but across the sky itself. A significant portion of the universe remains hidden behind our own galaxy. Roughly 20% of the observable sky is obscured by the dense disk of the Milky Way. In those directions, enormous concentrations of stars, gas clouds, and interstellar dust absorb visible light before it can reach telescopes on Earth or in orbit. The blockage is nearly total. Galaxies beyond the Milky Way may shine normally, yet their light vanishes while passing through the crowded galactic plane. Early astronomical surveys recorded this region as strangely empty because optical instruments could detect almost nothing there. Astronomers gave it a cautious name, the zone of avoidance, not because the universe itself avoided that region, but because human observation could not penetrate it. Maps of nearby galaxies contained a giant blind spot cutting directly across the sky, a missing section in humanity's attempt to chart the cosmos. But invisible does not mean empty. Infrared light, radio waves, and X rays can partially pass through the obscuring dust. As technology improved during the late 20th century, astronomers began probing deeper into the hidden region using instruments operating beyond visible wavelengths. Almost every survey found surprises. In 1996, the Rosat X-ray satellite revealed the Norma cluster concealed within the zone of avoidance. This massive concentration of galaxies helped explain part of the gravitational pull associated with the Great Attractor. Yet the discoveries kept growing larger. In 2016, astronomers using the Parkes Radio Telescope in Australia completed a major survey covering about 13% of the hidden region. Buried behind the Milky Way's dust, they uncovered the Vela supercluster, containing 883 previously uncatalogued galaxies. Until then, humanity had no idea it existed. The structure rivals some of the largest known concentrations of matter in the nearby universe, comparable in scale to the enormous Shapley supercluster farther beyond. Entire galactic systems had remained concealed simply because our own galaxy blocked the view. That realization changes perspective profoundly. Our cosmic maps often feel complete when viewed in textbooks or planetarium domes, but those maps still contain major uncertainties shaped by observational limits. The local universe has been reconstructed around a missing section, and every successful attempt to peer through that gap has revealed structures larger and more massive than expected. The blind spot continues shrinking slowly. Each new generation of telescopes penetrates a little farther through the dust, refining measurements of galactic motion and uncovering hidden flows of matter across enormous distances. Yet some regions behind the galactic center remain poorly explored even now. So, one of the least understood directions in the observable universe lies not at the edge of cosmic distance, but directly behind the bright, crowded heart of the galaxy we already call home. If we could rise far enough above galaxies themselves, the universe would stop looking scattered. The apparent randomness of stars and clusters would give way to something unexpectedly organized, a structure so enormous that it stretches across billions of light years, like the faint framework of a living system. Astronomers call it the cosmic web. Matter on the largest scales does not distribute itself evenly through space. Instead, galaxies gather into interconnected filaments, immense strands of matter linking dense regions together across unimaginable distances. These filaments intersect at nodes where galaxy clusters accumulate in tremendous numbers. Between them lie voids. Cosmic voids are enormous regions containing very little matter at all. Some span hundreds of millions of light years, while holding only a sparse scattering of galaxies. The largest confirmed example, the Botez void, stretches roughly 330 million light years across. Inside it, astronomers have identified only around 60 galaxies. Statistical models predict that a region of such size should contain thousands. Instead, vast expanses there remain almost empty, with distances between galaxies growing so extreme that an observer inside the void would see a profoundly darker universe than the night sky above Earth. The cosmic web emerged first as mathematics, before observation confirmed it. During the 1970s, computer simulations modeling gravity suggested that matter should naturally organize into filamentary structures over billions of years. In the 1980s, large redshift surveys began mapping galaxy positions in 3 dimensions by measuring how cosmic expansion stretches their light. The predicted architecture appeared clearly. Galaxies arrange themselves along gigantic walls and filaments, surrounding cavernous voids, forming patterns resembling neural networks or branching river systems viewed from above. The universe was not chaotic at the largest scales. It possessed structure, and that structure may be larger than anyone expected. In 2013, astronomers studying gamma ray bursts identified what could be the largest known structure in existence, the Hercules Corona Borealis Great Wall. This colossal arrangement of galaxies and matter may extend nearly 10 billion light years from end to end. Light itself would require almost the age of the universe to cross it. If confirmed fully, the structure challenges assumptions about how uniformly matter should distribute across cosmic distances. Some researchers continue debating whether it represents one coherent structure or several overlapping concentrations, aligned by perspective. But the web itself unquestionably exists. It also evolves continuously. Galaxies drift along filaments under gravity, flowing gradually toward dense nodes where massive clusters reside. Meanwhile, voids slowly empty further as matter drains away from their interiors toward surrounding structures. The entire network moves like a slow, cosmic circulation system, and beneath all of it lies something invisible. Dark matter, detectable only through gravity, forms the hidden scaffolding supporting the cosmic web. Ordinary visible matter alone lacks enough mass to create structures of this scale. Without dark matter anchoring the filaments gravitationally, galaxies would disperse far too easily for the web to maintain its shape across billions of years. So the largest architecture in existence depends primarily on matter. Humanity has never directly seen. By the middle of the 20th century, astronomers believed they understood the basic structure of galaxies. Stars orbited under gravity exactly as planets orbit the Sunday. Measure the visible mass, calculate the gravitational pull, and the motions should make sense. But the universe refused to cooperate. When astronomers studied how quickly stars moved inside spiral galaxies, the outer regions behaved strangely. Stars far from galactic centers traveled much faster than expected. According to the gravity produced by visible stars and gas alone, those outer stars should have drifted away into intergalactic space long ago. Yet they remained bound. This discrepancy appeared repeatedly. During the 1970s, astronomer Vera Rubin systematically measured rotation curves, graphs showing how orbital speed changes with distance from a galaxy's center across dozens of galaxies. Again and again, she found the same impossible pattern. The outer stars moved too fast. If visible matter were all that existed, galactic rotation curves should decline with distance, much like planets farther from the sun orbit more slowly. Instead, the curves stayed nearly flat. Something unseen was adding enormous amounts of gravitational pull. Rubin reached a radical conclusion. Galaxies must be embedded inside vast halos of invisible mass. This hidden material became known as dark matter because it neither emits nor reflects detectable light. Its presence reveals itself only through gravity, and there appears to be an extraordinary amount of it. Current cosmological measurements suggest ordinary visible matter accounts for only about 5% of the universe's total energy content. Dark matter contributes roughly 27%. Everything familiar, every planet, star, ocean, atmosphere, dust cloud, and living organism represents only a tiny fraction of what exists. The dominant structure remains invisible. Dark matter does not interact with light the way ordinary matter does. It neither absorbs photons nor scatters them. You could pass directly through a cloud of dark matter without seeing it, touching it, or noticing anything at all except its gravitational influence. But its exact nature remains unknown. It does not appear to consist of protons, neutrons, or electrons, the particles composing normal atoms. That means it lies outside the standard model of particle physics, the framework describing all currently known particles and forces. Physicists have proposed many candidates. One possibility involves WIMPs, meaning weakly interacting massive particles, hypothetical particles interacting so rarely with ordinary matter that detecting them becomes extraordinarily difficult. Other candidates include axions and sterile neutrinos, both theoretical particles predicted under certain extensions of modern physics. So far, none have been found. Experiments deep underground attempt to isolate detectors from cosmic radiation and environmental interference, searching for the faintest possible collisions with dark matter particles. The Large Hadron Collider at CERN has also searched extensively for evidence of WIMPs during high energy particle collisions. The silence persists. Yet dark matter's gravitational effects remain unmistakable. Without it, the outer Milky Way would disperse gradually into space. Spiral arms would not hold together. Galaxy clusters would unravel. The cosmic web itself could never have formed across billions of years. So every motion traced through this universe, from rotating galaxies to drifting superclusters, unfolds inside a gravitational framework built primarily from something humanity has never directly observed. For most of modern astronomy, gravity seemed destined to dominate the universe eventually. Every galaxy pulled on every other galaxy. Every cluster tugged inward. The expansion that began with the Big Bang should have been slowing gradually for billions of years, like a ball thrown upward against Earth's gravity. That expectation felt unavoidable. By the late 1990s, two independent research teams set out to measure exactly how quickly the cosmic expansion was decelerating. One group was led by Saul Perlmutter at Lawrence Berkeley National Laboratory. The other was led by Brian Schmidt and Adam Rees. Both teams studied Type Ia supernovae. These stellar explosions occur when white dwarf stars accumulate too much mass and detonate catastrophically. Because they reach nearly identical peak brightnesses, astronomers can use them as standard candles, objects whose true luminosity is known. Comparing true brightness to apparent brightness reveals distance across billions of light years. The method was elegant. Measure the distances of distant supernovae, compare them to redshift data showing how fast galaxies recede, and the slowing expansion rate of the universe should emerge naturally from the calculations. But the data refused to match expectation. The distant supernovae appeared dimmer than predicted. That meant they were farther away than existing models allowed. The only explanation consistent with the measurements was startling. The expansion of the universe was accelerating. Space itself was stretching faster over time instead of slowing under gravity. Both teams checked their calculations repeatedly for months because the conclusion contradicted decades of cosmological assumptions. Instrument errors were examined. Statistical methods were reworked. Independent measurements were compared. The result remained unchanged. In 2011, the discovery earned the Nobel Prize in Physics, but the mechanism driving the acceleration remains one of the deepest mysteries in science. Astronomers call it dark energy. Unlike dark matter, which pulls through gravity, dark energy appears to act as a property of space itself, causing empty space to expand outward intrinsically. The idea resembles Einstein's cosmological constant, a mathematical term he introduced in 1917 while attempting to construct a static universe model. Later, when expansion was discovered, Einstein reportedly called the constant his greatest blunder. But the universe may have returned it after all. Current measurements indicate dark energy constitutes roughly 68% of the total energy content of the cosmos. Ordinary matter and dark matter together form only a minority of what governs cosmic evolution. The consequences are profound. Galaxies beyond roughly 14.5 billion light years already recede from us faster than light, not because they move through space at impossible speeds, but because space between galaxies expands rapidly enough to carry them apart faster than light can bridge the gap. Those regions are permanently unreachable. No spacecraft could arrive there. No message sent today could ever catch them. Over immense stretches of time, more galaxies will cross beyond that cosmic horizon, fading permanently from view as expansion accelerates further. The observable universe slowly grows lonelier, and the force driving that isolation remains almost entirely unknown. Imagine standing anywhere in the universe and looking outward in every direction. No matter where you stand, distant galaxies appear to recede away from you. At first glance, this seems to imply a central point somewhere beyond the visible cosmos, a location where everything began moving apart. But there is no center. One of the deepest misconceptions in cosmology is the idea that the universe expands like debris from an explosion, matter rushing outward through pre existing emptiness from a single origin point. The real picture is stranger and far more difficult for human intuition to grasp. Space itself expands. Galaxies are not simply traveling through static emptiness away from a cosmic middle. Instead, the fabric separating galaxies stretches over time. Every sufficiently distant region moves away from every other region because the space between them continuously grows. This expansion occurs everywhere simultaneously. In 1929, astronomer Edwin Hubble confirmed this extraordinary behavior by measuring the light of distant galaxies. He discovered that their light shifted systematically toward longer red wavelengths, a phenomenon called redshift. The farther away a galaxy was, the stronger the redshift became. That pattern revealed a profound relationship. Distant galaxies recede faster than nearby ones because more expanding space exists between them. The rate of this expansion is described by the Hubble constant, which estimates how quickly recession velocity increases with distance. Current measurements produce an uncomfortable disagreement. Methods using nearby Cepheid variable stars and type Ia supernovae consistently estimate expansion at roughly 73 kilometers per second for every megaparsec of distance, with 1 megaparsec equaling about 3.26 million light years. But measurements derived from the cosmic microwave background suggest a lower value near 67. Astronomers call this discrepancy the Hubble tension. The disagreement appears too large to dismiss as ordinary measurement uncertainty. Something fundamental may be missing from current cosmological models. Perhaps an unknown particle influenced the early universe. Perhaps dark energy behaves differently over time than expected. Some researchers even suspect entirely new physics may eventually be required. The tension remains unresolved, and the expansion itself creates one of cosmology's strangest consequences. The observable universe extends roughly 93 billion light years across, despite the universe being only 13.8 billion years old. At first, this sounds impossible. How could light travel farther than 13.8 billion light years within 13.8 billion years? The answer lies in the stretching of space during the light's journey. While ancient photons traveled toward Earth for billions of years, the expanding universe simultaneously increased the distances involved. The destination kept moving farther away while the light crossed it. So when we observe the distant cosmos, we are not peering into static emptiness. We are looking through a dynamic geometry that stretches continuously between galaxies, clusters, and superclusters, carrying everything apart even while gravity struggles locally to hold structures together. The universe does not expand into anything, it simply expands. Long before galaxies existed, before stars ignited or planets formed, the universe was filled with opaque fire. Matter and radiation were packed together so densely that light could not travel freely for more than tiny fractions of a second before colliding with particles around it. The early universe glowed everywhere at once. For roughly 380,000 years after the Big Bang, electrons moved independently through the hot plasma, scattering photons continuously. Space remained brilliant but fogged, like sunlight trapped inside an endless storm cloud. Then the universe cooled enough for change. Electrons combined with protons to form the first hydrogen atoms. Suddenly, photons could move freely across space without constant interruption. The trapped light escaped in every direction simultaneously. That ancient radiation still exists. Astronomers call it the cosmic microwave background, usually shortened to the CMB. It fills the entire sky uniformly, arriving from all directions as faint microwave radiation with a temperature of approximately 2.725 Kelvin, colder than almost anything naturally found on Earth. It is the oldest light humanity has ever observed. Those photons began traveling nearly 13.8 billion years ago and have crossed expanding space ever since. Every time you look into the night sky, you exist inside a faint bath of ancient radiation left behind by the birth of the observable universe itself. But the CMB reveals more than age. Because the radiation surrounds us almost uniformly, it provides something extraordinarily valuable, a universal backdrop against which cosmic motion can be measured. If Earth remained perfectly motionless relative to this ancient light, the microwave background would appear exactly the same in every direction. It does not. One side of the sky appears slightly warmer, while the opposite side appears slightly cooler. The difference is tiny, only fractions of a degree, but measurable with extraordinary precision. The pattern comes from the Doppler effect. When we move toward incoming radiation, its wavelengths compress slightly, making it appear warmer. Radiation arriving from behind stretches slightly, appearing cooler. By measuring this dipole asymmetry across the sky, astronomers determined that the solar system moves relative to the cosmic microwave background at approximately 827 kilometers per second. That equals roughly 1.85 million miles per hour. The motion points roughly toward the constellation Hydra. It represents the combined result of Earth's rotation, Earth's orbit, the Sun's galactic motion, and the gravitational flows of surrounding cosmic structures layered together into one immense velocity. This is the closest thing physics possesses to an absolute speed. Not absolute in the classical sense imagined before relativity, but absolute relative to the oldest detectable frame of reference in existence, light released before stars, planets, or galaxies had even formed. And humanity discovered it accidentally. In 1965, engineers Arno Penzias and Robert Wilson worked at Bell Laboratories using a large microwave antenna designed for communications experiments. A persistent background hiss contaminated every observation they made. They checked the electronics repeatedly. They even cleaned pigeon droppings from the antenna suspecting contamination from nesting birds. Yet the noise remained constant across the entire sky. Eventually, they realized they were hearing the fading afterglow of the Big Bang itself. Far beyond the planets now, beyond the last meaningful pull of the sun's solar wind, a machine built in the 1970s continues moving through darkness with quiet persistence. Its name is Voyager 1. NASA launched the spacecraft in September 1977 during a rare planetary alignment that occurs only once every 176 years. Jupiter, Saturn, Uranus, and Neptune had lined up in a way that allowed a spacecraft to use each world's gravity as a slingshot, gaining speed without carrying impossible amounts of fuel. Voyager 1 used only two planets for its acceleration. Jupiter bent its path and increased its velocity dramatically. Saturn did the same. Each encounter transferred a tiny fraction of orbital momentum from the giant planets into the spacecraft itself, boosting it onto a trajectory fast enough to escape the solar system entirely. The speed remains extraordinary. Relative to the Sun, Voyager 1 travels at approximately 38,000 miles per hour. At that velocity, you could cross the continental United States in less than 6 minutes. Yet space is so enormous that even this speed becomes painfully slow across interstellar distances. As of 2024, Voyager 1 sits roughly 24 billion miles from Earth. Radio signals travel at the speed of light, the fastest speed possible in the universe. Even so, a message sent from Earth takes more than 22 hours to make a round trip between mission control and the spacecraft. Communication unfolds with immense patience. Despite moving faster than any previous human-made object at launch, Voyager 1 would still require approximately 73,000 years to reach Proxima Centauri, the nearest star to the Sun. If it happened to be traveling in that direction, it is not. But distance was never the only purpose. In August 2012, instruments aboard Voyager 1 detected a sudden transformation in its surrounding environment. Charged particles from the Sun dropped sharply. Particles originating from interstellar space increased instead. The spacecraft had crossed the heliopause. The heliopause is the outer boundary where the solar wind, a stream of particles flowing outward from the Sun, loses its strength against the thin gas between the stars. Beyond that boundary lies interstellar space. Humanity had finally reached it. And still the spacecraft continues speaking. Its transmitter is astonishingly weak now. By the time Voyager's signal reaches Earth, astronomers must detect energy approximately 20 billion times fainter than the power used by a typical watch battery. Yet, the whisper remains detectable. Attached to the spacecraft is something strangely intimate, a gold-plated copper phonograph record assembled under the direction of Carl Sagan. Encoded onto it are greetings in 55 languages, music from 27 cultures, whale songs, footsteps, surf, rain, heartbeat rhythms, and the cry of a newborn child. Not because scientists expected anyone to find it, but because sending a silent machine into the galaxy without some trace of ourselves felt incomplete. A drifting object crossing interstellar darkness seemed to require memory, even if no one would ever hear it. After tracing every layered motion around us, from planetary orbits to galactic flows, we eventually arrive at a boundary that reshapes the meaning of speed itself. The speed of light changes everything. Earth moves through the universe at roughly 1.85 million miles per hour relative to the cosmic microwave background. That velocity feels enormous when compared to daily human experience. But light travels at approximately 670 million miles per hour, roughly 360 times faster. Nothing with mass can reach that speed. Not a spacecraft, not a particle accelerator, not even a single atom. This limit is not an engineering problem waiting for future technology to solve. It appears woven directly into spacetime itself. Albert Einstein described this through special relativity in 1905. As an object accelerates closer to light speed, its inertia, meaning resistance to further acceleration, increases dramatically. More energy becomes necessary for every additional increase in velocity. Near light speed, the required energy rises toward infinity. The wall cannot be crossed. But relativity produces stranger consequences than limitation alone. Time itself changes. A moving clock runs more slowly relative to a stationary observer, an effect called time dilation. This is not theoretical speculation. Atomic clocks flown aboard aircraft tick measurably slower than identical clocks remaining on Earth's surface. The difference is tiny but real, directly confirming relativity through experiment. You encounter the same effect every day without noticing. GPS satellites orbit Earth at approximately 14,000 kilometers per hour while also existing farther from Earth's gravitational field. Velocity slows their clocks slightly. Reduced gravity speeds them up slightly. Both effects must be corrected continuously using relativistic equations. Without those corrections, GPS positions would drift by approximately 11 kilometers every day. Modern navigation depends on Einstein being correct, but the speed of light imposes another consequence, even more profound. Every observation in astronomy is an observation of the past because light requires time to travel. Nothing is seen instantly. Sunlight reaching your eyes tonight left the sun 8 minutes and 20 seconds ago. If the sun somehow disappeared, Earth would continue orbiting normally for more than 8 minutes before darkness arrived. Distance delays reality. The Andromeda Galaxy appears as it existed 2.537 million years ago. When that light began its journey toward Earth, early Homo habilis populations were shaping primitive stone tools across East Africa. The universe you see is never current. Even nearby stars appear slightly outdated because their light spent years crossing interstellar space before reaching you. Greater distances deepen the delay. Telescopes become time machines automatically, whether intended or not. The James Webb Space Telescope now detects galaxies whose light departed when the universe was only a few 100 million years old. Those systems may no longer exist in their original forms. Some may have collided completely. Others may have exhausted their star formation billions of years ago. Yet their ancient light continues arriving now, carrying frozen images from an earlier cosmic era across expanding space. At the largest scales, motion becomes inseparable from time itself. None of the velocities we have followed can be sensed directly by human perception. The universe provides no wind from motion through space, no vibration beneath your feet, no visible streaking stars outside the atmosphere. Everything must be measured indirectly. Astronomy became a science of motion through light itself. Every technique used across cosmic distance relies on extracting hidden information from faint photons arriving after journeys lasting years, millions of years, or even billions. The first essential tool is Doppler shift. When a light source moves toward you, its wavelengths compress slightly, shifting toward the blue end of the spectrum. When it moves away, the wavelengths stretch toward red. By measuring the exact displacement of spectral lines, astronomers can calculate velocity with remarkable precision. A star's motion becomes visible mathematically. But velocity alone means little without distance. Nearby stars require another method entirely, one rooted in Earth's orbit around the Sunday. This technique is stellar parallax. As Earth moves from one side of its orbit to the other across 6 months, nearby stars appear to shift slightly against the much more distant background stars. The shift is tiny, often smaller than the apparent width of a coin viewed from thousands of kilometers away. Yet the geometry reveals distance directly. Once astronomers know both distance and angular motion across the sky, they can reconstruct a star's true movement through three-dimensional space rather than merely along our line of sight. Beyond nearby stars, parallax becomes too small to measure reliably. Another tool takes over there. Certain stars, called Cepheid variables, brighten and dim rhythmically over predictable periods. In 1908, Henrietta Swan Leavitt discovered that the pulsation rate of these stars directly corresponds to their intrinsic brightness. A slowly pulsing Cepheid shines more powerfully than a rapid one. By comparing true brightness to apparent brightness, astronomers determine distance across millions of light years. Her discovery transformed scattered observations into a measurable cosmic scale. The universe suddenly became navigable. Farther still, astronomers rely on Type Ia supernovae, exploding white dwarf stars that reach nearly identical peak luminosities. Because their brightness is so consistent, they function as standard candles visible across billions of light years. These explosions revealed accelerating cosmic expansion in 1998. Modern astronomy layers all these methods together carefully. Each technique covers a different range of reliability. Their overlap regions act as cross-checks, verifying measurements independently before extending farther outward. Precision grows cumulatively. The most ambitious mapping effort yet arrived in 2013 with the launch of the Gaia spacecraft by the European Space Agency. Gaia measures stellar positions, distances, and motions with sub-micro-arcsecond precision, accuracy so fine it could detect the width of a human hair from thousands of kilometers away. It has already mapped more than 1.8 billion stars. But above all these methods sits the cosmic microwave background itself. The CMB dipole measurement does not compare Earth to nearby stars or neighboring galaxies. It measures our motion relative to the oldest observable light in existence. A universal frame emerges from ancient radiation. For most of recorded history, stillness felt obvious. You stand on the ground, and nothing beneath you seems to drift or sway. The sun rises. The stars wheel overhead. The world appears calm and fixed, while everything else circles around it. Entire civilizations built their cosmologies from that immediate sensation. Earth stood at the center because human experience seemed to confirm it every day. In the 4th century BCE, the Greek philosopher Aristotle tried to explain that apparent stillness with logic. If Earth moved, he argued, motion should reveal itself constantly. A stone dropped from a tower should fall behind the tower's base because the ground would shift during the fall. But the stone landed straight down. To Aristotle, the conclusion seemed unavoidable. Earth did not move. His reasoning lacked inertia, the principle that moving objects carry their motion with them, yet within the physics of his era, it formed a remarkably durable framework. But not everyone accepted the stationary Earth. In the 3rd century BCE, Aristarchus of Samos proposed something radically different. He suggested the sun occupied the center while Earth traveled around it. The idea arrived almost 2,000 years too early. Without instruments capable of detecting Earth's motion directly, heliocentrism remained an intellectual curiosity rather than a convincing reality. That changed slowly. In 1543, Nicolaus Copernicus published De Revolutionibus Orbium Coelestium, placing the sun at the center of the planetary system once again. The mathematics became cleaner. Planetary motions suddenly made more sense, yet the emotional consequences were enormous. Earth transformed from cosmic anchor into one moving object among many. The shift deepened in 1609 when Galileo Galilei pointed a handmade telescope toward Jupiter. There, circling the distant planet, were four moons, tiny moving worlds. Their existence shattered a central assumption of geocentrism, the belief that everything in the heavens revolved around Earth alone. Galileo published his observations quickly. Opposition followed just as quickly. In 1633, the Roman Inquisition placed him under house arrest, where he remained until his death 9 years later. Even then, many people still argued Earth's motion could not truly be felt or measured. The proof arrived piece by piece. In 1728, English astronomer James Bradley discovered stellar aberration, a subtle shift in starlight caused by Earth's orbital motion. The effect resembled rain appearing to slant toward you when you run forward through a storm. The stars themselves had not changed direction. We had. More than a century later, in 1851, Léon Foucault suspended a pendulum beneath the dome of the Pantheon in Paris. As crowds gathered below, the pendulum's swing slowly rotated throughout the day. The pendulum was not turning. Earth was rotating beneath it. People watched motion reveal itself in real time, directly under their feet. From Aristotle to Foucault, over 2,000 years passed before humanity finally learned how to detect the movement carrying us through space every second of our lives. Sit quietly for a moment, and your body reports almost complete stillness. Your breathing slows. The floor feels stable beneath you. Nothing in your senses suggests motion of any kind. Yet, at that same instant, Earth rotates at roughly 1,000 miles per hour near the equator, orbits the Sun at 67,000 miles per hour, circles the Milky Way at more than 500,000 miles per hour, and drifts through the cosmic microwave background even faster still. But none of that produces the slightest sensation. The reason lies in a principle first formalized by Isaac Newton in the 17th century. Newton's first law states that an object moving at constant speed in a constant direction experiences no net force. Without a force acting to change the motion itself becomes physically undetectable from rest. Uniform movement and stillness feel exactly the same from inside the system experiencing them. Every molecule around you shares Earth's motion. The atmosphere moves with the planet. The oceans do too. Buildings, trees, birds, clouds, and your own bloodstream all travel together as part of the same continuous frame. You are not rushing through a stationary universe. You are embedded within a moving environment that carries everything along simultaneously. Only changes in motion become visible to the body. Acceleration matters, deceleration matters, turning matters. A passenger resting in a commercial aircraft cruising at 575 miles per hour can balance a cup of coffee calmly on a tray table. Yet, a sudden stop in a car traveling 30 miles per hour throws the body violently forward because the motion changes abruptly. Your body senses forces, not speed. Even Earth's rotation creates only a faint physical effect. At the equator, centrifugal force, the outward tendency caused by rotation, slightly counteracts gravity. As a result, you weigh about 0.3% less there than at the poles. The difference is real but subtle, amounting to only a few ounces for most people. Earth's orbital motion around the Sun contributes an even smaller effect. Instruments can measure it precisely. Human senses cannot. This confusion about motion often extends into orbit itself. Astronauts aboard the International Space Station appear weightless, but gravity has not vanished there. At an altitude of roughly 250 miles, Earth's gravity remains about 90% as strong as on the surface. The station and its crew are simply falling around Earth continuously, moving sideways fast enough to keep missing the ground. But if you stood aboard a spacecraft drifting between galaxies at millions of miles per hour, no internal sensation would reveal it. Without an outside reference point, the experience would feel indistinguishable from perfect rest. The universe conducts all this motion in silence. Human senses evolved to detect falling branches, shifting ground, and approaching storms across distances of meters and moments of seconds. Against the deeper motions of the cosmos, the body remains almost completely blind. Before anything else in the solar system disappears into scale, there is a single photograph that quietly reframes everything. It was taken on February 14th, 1990, when Voyager 1, now nearing the edge of the solar system, was commanded by Carl Sagan to turn its camera back toward home for one final image. From a distance of about 3.7 billion miles, Earth appears as a single pixel, a pale blue dot suspended in scattered sunlight. No continents are visible, no storms, no borders. Only a faint point of light that requires precise knowledge to even locate within the frame. The surrounding darkness dominates the image. Sunlight scattered through the optics takes up more visual presence than the planet itself. The entire human world, reduced to something smaller than structure, smaller than detail, smaller than recognition. But that was never the point of the photograph. Sagan later described it as a mote of dust suspended in a sunbeam, not as poetic exaggeration, but as a correction of scale. A reminder that every civilization, every conflict, every ocean and mountain exists on something almost vanishing in cosmic terms, something easily missed unless it is already known to be there. The image carries no scientific measurement of Earth's geology or atmosphere. It was not designed to refine data or improve models. It was taken for perspective alone. A deliberate act of looking back from the farthest human reach at the place from which all human history emerged. And in that single pixel, everything described so far is still happening at once. That dot rotates at roughly 1,037 miles per hour. It orbits the Sun at about 67,000 miles per hour. It moves around the galactic center at more than 500,000 miles per hour. It is also being drawn toward a larger cosmic flow at over 1 million miles per hour, all motions layered together, continuous and unbroken. It has not paused for any of it. For 4.5 billion years, this combined motion has carried a thin surface of rock, ocean, and atmosphere through changing cosmic environments. Ice ages formed and vanished. Continents split and collided. Life appeared, diversified, and learned to observe its own setting. But only in the last 300,000 years has one branch of that life looked upward with questions that include numbers, distances, and directions, asking not just where it is, but how fast it is moving while it asks. The pale blue dot does not answer. It only continues. Long after human history becomes indistinguishable from geology, Earth will still be in motion. The same layered speeds that define its present will continue, but their structure will slowly shift as the system holding them together changes from within. The first shift is subtle. The sun is losing mass continuously through solar wind, a steady outflow of charged particles that drift away into space. As this mass escapes, The sun's gravitational grip weakens slightly. Earth responds by drifting outward, its orbit expanding over immense spans of time. The change is gradual, almost imperceptible on human scales, but it accumulates. In about 1 billion years, that accumulation becomes critical. By then, the sun's luminosity, the total energy it emits each second, will have increased by roughly 10%. That small rise will be enough to destabilize Earth's climate system. Oceans will begin to evaporate into the atmosphere. Water vapor, itself a powerful greenhouse gas, will trap more heat, amplifying the process. A runaway greenhouse effect will unfold, transforming the planet into a world where liquid water can no longer persist on the surface. Life, at least in complex forms, will end long before the final stage arrives. But the orbital motion continues. Around 5 billion years from now, the Sun will exhaust the hydrogen fuel in its core. Nuclear fusion will shift into surrounding layers, and the star will expand dramatically into a red giant, growing perhaps 100 to 200 times its current size. Mercury and Venus will almost certainly be engulfed. Earth's fate is less certain. It may be consumed, or it may drift just beyond the expanding stellar surface, stripped and scorched into a barren remnant. Beyond the solar system, motion becomes quieter but more persistent. The Milky Way's overall structure remains stable across tens of billions of years. Stars continue orbiting the galactic center in vast, slow loops. Even the solar system's path through the galaxy remains largely unchanged unless disturbed by an unlikely close encounter with another star. But stability does not last forever. In roughly 4.5 billion years, the Andromeda Galaxy will merge with the Milky Way. This collision will not resemble impact in any everyday sense. Instead, it will be a gravitational restructuring across hundreds of millions of years. Simulations suggest the Sun may be relocated to a completely different region of the new galaxy, sometimes called Milkomeda. Its orbit will be rewritten. On even longer scales, motion itself fades. Over trillions of years, galaxies exhaust their gas and stop forming stars. Existing stars burn out one by one. Black holes slowly lose mass through Hawking radiation, a theoretical process where quantum effects allow them to emit energy and evaporate over unimaginable timescales. Far beyond that, even matter may not remain stable. Protons could decay, particles disperse, energy spreads thin across an expanding, cooling universe approaching thermodynamic equilibrium, a state where no usable energy differences remain to drive motion or change. Everything that moves now will still have moved, but nothing will move in the same way forever. In the quiet between star fields, distance begins to feel like structure, not emptiness, but arrangement. We look outward and see a galaxy that is densely packed by human intuition, yet statistically sparse in connection, with hundreds of billions of stars separated by gaps measured in light years. Within that scale, every assumption about company in the universe begins to stretch. The Milky Way alone contains roughly 200 to 400 billion stars, each one a potential sun. Many host planets. Some sit in stable, habitable zones where liquid water could persist long enough for chemistry to grow complex. The numbers suggest abundance. They suggest repetition. But suggestion is not evidence. This tension was captured in a simple question at a lunch table in 1950 when Enrico Fermi asked, "Where is everybody?" No ceremony, no calculation at first, just a recognition that expectation and observation refuse to align. The universe appears prepared for life, yet silent. We extend that silence across time. The galaxy is about 13.6 billion years old, long enough that even slow expansion could have filled it with overlapping waves of technology. A civilization moving at only a fraction of light speed could, in theory, cross the Milky Way in a few million years. The time available is vast, the absence remains. Search programs continue listening. SETI, the search for extraterrestrial intelligence, has been scanning radio frequencies since 1960, using increasingly sensitive instruments tuned to patterns that would not occur naturally. In 1977, one detection stood out: the WOW signal, recorded by astronomer Jerry Eman at the Big Ear Telescope in Ohio, lasted 72 seconds. It showed a narrow-band structure that briefly matched expectations for an artificial origin. It never repeated. It never explained itself. But even anomalies like that fade back into statistical noise. No confirmed transmission has followed. No artifact has been identified beyond Earth. No structure in starlight carries an unambiguous signature of engineering. The silence holds across every direction we can measure. From this perspective, explanations multiply. Life may be rare in its first step, emerging only under conditions far narrower than we assume. Or complex life may rarely survive long enough to develop detectable technology. Civilizations may turn inward or outward in ways that do not emit signals we recognize. Or there may be limits to expansion itself, imposed by physics, by resources, or by choices we cannot yet model. And yet, every star continues its motion. Each one orbits the same galactic center, drawn along spiral arms shaped by gravity and time. They all move through the same background described across this journey, through filaments, voids, and invisible mass. If other observers exist, they are part of that same motion, moving as we are through a galaxy that carries everything forward at once, and still the radio sky remains quiet. At some point in the attempt to understand motion on cosmic scales, numbers stop behaving like measurements and start behaving like resistance. We do not struggle because the data is unclear. We struggle because the mind was never designed to carry it. The human brain evolved for immediate survival, tuned to distances of a few dozen meters and decisions measured in seconds. It tracks faces, footsteps, weather shifts, the angle of light across familiar terrain. It does not naturally encode millions of light years as anything more than abstract symbols without physical weight. Neuroscientist Paul Slovic described one part of this limitation as psychic numbing, where emotional response collapses as numbers grow larger. One tragedy is felt, 100 becomes vague, 1 million becomes almost featureless. The meaning flattens, even when understanding remains intact. But this flattening becomes more extreme when applied to the universe itself. A speed like 1.85 million miles per hour and a speed like 67,000 miles per hour both register as simply fast. The difference exists mathematically, yet it does not anchor emotionally. The mind loses grip on proportion. Richard Feynman often pointed toward a deeper difficulty, not ignorance, but split perception. The ability to hold two models at once, one built from human experience and one built from physical law. Both are correct within their domains. Both feel incompatible in the same moment. One way to test this tension is to compress time. Human civilization, from early river cities to modern satellites, spans roughly 5,000 years. During that same interval, the solar system has moved through only a fraction of a single galactic orbit, so small it approaches zero when written as a percentage. The scale does not stretch intuition, it erases it. Another compression works through space. If the Milky Way were reduced to the size of North America, the entire solar system would shrink to something smaller than a coffee cup. Earth would not be a visible object at all. It would exist below the threshold of perception inside that container. Even the night sky misleads through proximity. Every star, visible without instruments, belongs to a local bubble only a tiny fraction of the galaxy's width. It feels complete because it is bright. But brightness is not structure. Beyond that small region, the galaxy continues without interruption. Not empty, not distant in the way a void feels distant, but densely populated with stars, systems, and motion on scales no senses can directly detect. And all of it is moving, quietly, continuously, together. In earlier worldviews, location carried weight far beyond geometry. Where something existed was also what it meant. A position in space could define importance, purpose, even destiny. The sky was arranged like a hierarchy, and Earth sat at its base or its crown, depending on the culture interpreting it. For more than 1,400 years in the Western tradition, the Ptolemaic system held that structure in place. Earth stood motionless at the center of nested spheres, carrying the sun, moon, planets, and stars. It was not only a model of motion, but a model of significance, where centrality implied priority. The universe was organized around a human reference point. That structure eventually dissolved. Modern cosmology replaced it with something far less intuitive. There is no center to expansion, no privileged position in space, no cosmic origin point from which everything spreads outward. Every location is equally valid in describing the structure of the universe. But removal of a center does not remove consequence. Earth still occupies a precise orbit around a specific star, within a particular region of a spiral galaxy, at a distance that allows liquid water to persist across billions of years. The absence of centrality does not erase specificity, it reframes it. This is where the anthropic principle becomes relevant, a concept explored in different forms by philosopher Nick Bostrom and others. It states that the universe we observe must be compatible with our existence, because observation itself requires conditions that permit observers. It is not evidence of design, it is a filter on what can be seen. From that perspective, Earth's properties are not random in their outcomes. Its axial tilt produces seasonal cycles that regulate climate variation. Its orbital distance stabilizes energy input from the Sunday. Its position within the Milky Way places it between spiral arms, where stellar density is lower and catastrophic events occur less frequently over long periods. Each factor contributes quietly to continuity. Even the broader architecture matters. The solar system's orbital resonances reduce long-term chaos in planetary motion. The moon stabilizes Earth's axial tilt over geological time, preventing extreme climatic swings. These are not isolated features. They interact as a system of conditions that allow complexity to persist. Seen this way, home is not defined by central placement. It is defined by stability within motion, by conditions that remain coherent long enough for something to exist and continue existing. The universe offers no fixed center to orient meaning around, but it does offer regions where structure holds, where motion does not tear everything apart, where time can accumulate into history. And we find ourselves in one of those regions, moving through space that does not privilege us, yet permits us to be here. Before any thought forms, there is material continuity. The body does not begin with identity. It begins with atoms arranged into temporary structure, each one older than any organism that has ever carried it. Nothing here is newly created in the human sense. Everything is assembled from earlier cosmic events. The elements that define biological life, carbon, nitrogen, oxygen, iron, are not primordial. They are forged in stellar interiors through nuclear fusion, the process where light atomic nuclei combine under extreme pressure to form heavier ones, releasing energy across millions of years. When massive stars exhaust their fuel, they collapse and explode in supernovae, scattering those elements across space. From there, nothing remains stationary. Those atoms drift through interstellar clouds, join new star systems, cycle through planetary formation, disperse again, and re enter new structures over spans of billions of years. They are not assigned to one identity. They participate in repeated cosmic recycling. At this moment, the matter that composes you is still in motion, not metaphorically, but physically measurable. It rotates with Earth at about 1,037 miles per hour. It orbits the Sun at roughly 67,000 miles per hour. It travels with the solar system around the Milky Way at more than 500,000 miles per hour. It is also carried toward the region known as the Great Attractor at about 1.3 million miles per hour. And all of this sits within a broader motion of approximately 1.85 million miles per hour relative to the cosmic microwave background. But none of these velocities are separate from you. They are the motion of the same structure you inhabit. There is no division between observer and system at this scale. The body is not moving through the universe as an external passenger. It is one configuration of the universe moving through itself. Physicist Brian Greene has described this as a distinction between experience and mechanism. The universe does not possess awareness of its own evolution in a global sense. It follows physical law without perspective. Yet, within that same framework, local regions of matter organize into complexity that can observe, measure, and reflect. On a small planet, within a narrow window of cosmic time, matter briefly forms patterns capable of recognition. Cells, neurons, perception. These structures do not stand outside the system. They emerge from it. And in that emergence, something unusual occurs. The universe develops a way of representing its own motion internally, not in equations alone, but in lived awareness. A configuration of atoms becomes capable of asking what those atoms are doing. You are not separate from the motion described across this entire sequence. You are one of its expressions. Before light enters your room, motion has already accumulated across scales too large to sense. Earth continues its orbit at a pace that carries it roughly 1.6 million miles through space in a single night. Nothing changes in appearance. Everything changes in position. The solar system follows that same curve around the galactic center, adding nearly 4 million miles to its path over the same span of time. It is not moving through empty space alone, but through a gravitational structure shaped by billions of stars, all of them following their own arcs in silent coordination. Beyond that, the Milky Way itself drifts through the local cosmic environment, slowly drawn toward the Great Attractor, a vast region of gravitational influence, located roughly 150 to 250 million light years away. It is partially obscured by our own galaxy, still being mapped, still not fully understood in its structure or extent. But none of this motion produces sensation. No vibration reaches the air. No shift enters the room where you are. The body remains still relative to its surroundings, even as it participates in speeds that would be unimaginable if experienced in isolation. Across 13.8 billion years of cosmic history, Earth has completed roughly 20 full orbits around the Milky Way. In that same span, it has rotated on its axis about 1.6 trillion times. Each rotation carried the surface from night into day and back again, without interruption, without witness for most of its duration. Before perception existed, motion was already present. Stars formed, collapsed, and scattered their elements long before there was any structure capable of registering their light. The universe did not wait for observers. It continued assembling complexity until observation became possible within it. And even now, that pattern persists. Speed remains real. Scale remains real. Silence remains real. They are not abstractions. They are the environment itself, extending in every direction, independent of awareness. Within that environment, there is a small planet where temporary arrangements of matter have become capable of noticing, not controlling, not stepping outside, only noticing. That awareness lasts briefly compared to the structures it observes, but it is part of the same unfolding system. Everything described across this journey continues without interruption. The drift of galaxies, the pull of unseen mass, the expansion of space itself, all proceeding whether or not it is measured. Rest is simply a local condition within a moving universe, and while it lasts, the motion continues unchanged, vast and indifferent, yet precisely ordered. The universe does not pause. It only carries on,